Okay, in class today, we became bogged down on this particular calculation where we're looking at butting up two different materials together and looking at the heat flow. All right, so what I did in class, we were trying to keep track of the dimensions and making sure everything was dimensionally consistent. And so it made the problem seem harder than it really is because I spent a lot of time discussing the units. Okay, so let's take a different approach. Recall, here's the problem. We have one material A that's wood, okay, and it's 2 inches thick. And then we have another material B that's brick, and it's 6 inches thick. And those are butted up together. We have the temperature on either side, and so we're interested in the flow of heat, okay? And so what we know for the units here are that we're using English units, and so we'd be looking at BTU per hour, all right, and then per feet per degree Fahrenheit. So that's conductivity of heat in English units. Okay, so we talked about in class, it's a one-dimensional problem, which means we're really just worried about the cross-sectional area being 1. Okay, so A is equal to 1 square foot. All right, so that's how we normalize by the area, so that's effectively how you do that. Okay, so we talked about the idea of thermal resistance. We also talked about the idea of having consistent set of units. Okay, so what we can do is we can start out and we have 18 degrees Celsius, all right. We could immediately convert that over into Fahrenheit. So do that conversion, 18 degrees Celsius works out to 64.4 degrees Fahrenheit. And then same thing with the second temperature, the 6 degrees. 6 degrees Celsius converts over to, I have it down on a piece of paper, 42.8 degrees Fahrenheit. Okay, so that immediately gets that particular parameter into the correct units. All right, then we have delta x1 for the first material. That's 2 inches, so convert 2 inches to feet, and we would get 0.17 feet. All right, and the second material, 6 inches, convert that to feet, and we'd get 0.5 feet. All right, so now we have everything in the right units. We can start taking a look at the flow of heat. And we talked about this in terms of thermal resistance, and so I'm going to draw the electrical symbols for resistance. Here's R1, here's R2. Okay, and R1 is simply delta X divided by K times A. But remember, we're looking for A to be 1 in this example. So plugging in 0.17 in the problem statement, the thermal, somewhere earlier in the problem, we gave the thermal conductivity of wood, and it turns out that for wood, K is 0.174. Okay, so we divide by 0.174, and we get 0.96 for the thermal resistance for wood. Okay, doing the same thing for R2, it's thicker, it's brick, so that's going to be 0.5, and then the thermal conductivity is 2 times K, 2 times 0.174. And we do that calculation, and we get 1.44. So notice I'm not keeping track of the units just to make things be a little simpler. We have already established that these are the correct units, and so at the end we will plug the units back into the equation. Okay, so here's what we have so far. We have 0.96, we have 1.44, and we know what the delta T is between here and here. It's going to be T2 minus T1. Okay? And so Q, in this case, is going to be equal to the temperature difference. All right, so that's minus the 64.4. I'm sorry, T2 is 42.8 minus 64.4. All right, divided by the total resistance, right? You combine resistors in series, so this would be 0.96 plus 1.44. You plug that into your calculator, you get 9. Okay, so what are our units? Well, because we started with English units and we had K in BTUs per hour per foot per degrees Fahrenheit, that means Q is going to be 9 BTUs per hour. Okay, example number 2B. We're switching things up a bit. We still have the two pieces of material where this is wood, and what we know is at this point this is 18 degrees, but I can convert that to Fahrenheit, so 64.4. And then the intermediate temperature, the temperature between the wood and the brick, is going to be 10 degrees Celsius, which is 50 degrees Fahrenheit. And what we want to know is, what is T2? Okay, so if we think about that, what we know here is that there's two resistances to heat, the wood and the brick. And we know the value for wood is 0.96. The value for brick is 1.44. All right. So what I can get is, if I know this heat flow Q, I can figure out this delta T. Okay, here's Ti, here's T2. So this particular delta T, I can get it because it's just it's like Ohm's law. It's Q times the resistance. Okay, and by the same token, I know that this temperature is 64.4. This temperature is 50. So I know the temperature difference. I can calculate Q. All right. So it's like knowing the voltage across one resistor in series. You can then calculate the current. All right. Once you know the current, you can calculate the voltage drop across the next resistor. It's the same idea, only we're using heat flow and temperature. All right. So Q is going to be delta T divided by 0.96. All right, we know which direction it's flowing. The delta T is going to be 14.4. The 50 minus 64.4 with a negative sign gives me positive 14.4 divided by 0.96, and I get Q is 15, and that would be in BTUs per hour. All right, so that helps me. I know what Q is. All right, so I'm going to move this and put it to the side. All right, so put that up here. We know Q is 15 BTUs per hour. All right, next, since this is 15 coming this way, all right, the delta T across the brick is going to be 15 times 1.44, which is 21.6. Okay, so that's going to be the delta T in Fahrenheit, because that's the unit system we're using. So if Ti is 50, then T2 is going to be 50 minus that delta T, which is 28.4 degrees Fahrenheit. Okay, so that's the answer for the second part. So you see, if you know that you have dimensionally consistent units, you can more quickly get to the answers, okay, because we're not keeping track of units every step of the way, but we know it's going to all work out in the end. Okay, in the last example that I'm going to do in this video, we now assume that we have the temperature at one side of the wood is going to be our usual 18 degrees, which we know is 64.4 Fahrenheit. And then we're going to keep the intermediate temperature here at 10 degrees Celsius, 50 degrees Fahrenheit. And then we want to figure out how thick should the brick be, to get this down to 0 degrees Celsius. Okay, and so we know 0 degrees Celsius is 32 degrees Fahrenheit. Okay, so how do you approach this problem? Okay, well, we know that these are the same numbers from the previous part. So I know this Q flowing through here, the heat flow is 15 BTUs per hour. All right, so I now have a delta T across the brick. The delta T, I put that at 0 degrees, that should have been 32 degrees. The delta T is going to be 18 degrees. Okay, so I want 18 to be equal to Q, which is 15, times the new R. Okay, so I can solve for R. R is going to be 18 divided by 15. Okay, so 18 divided by 15 is 0. I'm sorry, it's not 0. Hang on, let me calculate that. I didn't write that down. 18 divided by 15 is 1.2. Right? So I know the resistance of the second material, the thermal resistance, is 1.2. Okay, and so from there, we knew that that was delta X divided by 2 times 0.174, right? Because we said brick had twice the thermal conductivity of wood. Okay, and the area that we're using in this problem is 1. Okay, so I know that should be equal to 1.2. Okay, I can then solve for delta X. 1.2 times 2 times 0.174 gives me 0.4176 feet. All right, if we wanted to convert that to inches, we'd multiply by 12. And what you get is 5.0 inches. Okay, so that's the answer to the third part of this problem.